Hello students, so in this lecture we shall be discussing about spin, resonance, spectroscopy. Now, in short it is called SRS. Now all electrons have spin half. This is equal to half for the electrons, and they have an angular momentum, spin angular momentum, S into S plus 1 H cross. So that makes it root 3 by 2 H cross. Many molecules also possess spin, although angular momentum varies from molecule to molecule. The simplest molecule is that of an hydrogen atom. We know that. And it consists of one particle, one electron and one proton. And the protonic mass of the proton is 1.6 into 10 to the power minus 27 kg, and charge is of course 1.6 into 10 to the power minus 19 coulombs. Now this proton has also got a spin half. A charged particle spinning about an axis produces magnetic dipole. So when a charged particle is spinning about an axis, so it produces a dipole. So a dipole is actually we can consider it as a tiny bar magnet. So a spinning particle acts as a tiny bar magnet placed upon the spin axis. Now the size of the dipole should say the size of the dipole or it is equivalent to the strength of the magnet. I can write mu is equal to Q by 2m into I, and that is equal to I is the angular momentum associated with a nuclear spin. So we write Q by 2m into I into I plus 1, or it is also called an isospin H cross. Now this is the unit of this is ampere per meter square. Now if Q and M are charge and mass of the particle, we know that, and ampere per meter square is equivalent to joules per temperature, or joules per Tesla. And the magnetic moment mu is can be written as then Q by 2m, or I should say as QH by 4 pi m I into I plus 1 root joules per Tesla. Now, when we remove the friction between then the electrons and holes are the point charges, so we can write mu is equal to G QH by 4 pi m root I into I plus 1 joules plus Tesla. We can also call it a symbol G, look at capital G. This is the Landé splitting factor. It's the value which depends upon the quantum state of the electron. So for electrons, mu is equal to minus G beta I into I plus 1 joules plus Tesla, where beta is equal to 2h cross by 2m or QH by 4 pi m. It's the Bohr monotone for the unit of magnetic moment. Magnetic dipoles are conventionally expressed in terms of nuclear magnetic moment. So as we have an atomic magnetic moment, similarly, if you BH will be equal to E H cross by 2mp. Now beta was Q H cross by 2m. So it has been replaced by, for the nucleus, it has been replaced by this quantity, whereas Q has been replaced by Q has been replaced by E, and mass of electron has been replaced by mass of the proton, and its value is so you can see that the Q has been replaced by E, and H and MP has been replaced by, or M has been replaced by MP. Now its value is 5. 5 into 10 to the power, 5.050 into 10 to the power minus 27 joules per Tesla. So, nucleus of mass capital M and charge PE can have magnetic moment equal to G PE by 2m I into I plus 1 which cross, which is equal to G MP P E divided by M into beta N I into I plus 1 H cross. Now, if we take I is equal to 1, then I is equal to I into I plus 1, the mod of I, the value of I, H cross, is equal to root 2 units, H cross. So, and the Z component of I is split up into two directions if magnetic field is applied. So if magnetic field is applied, it will split up into 0 plus 1 and minus 1. Minus 1 and plus 1 for I is equal to 1. So that is IZ. So IZ is equal to minus 1. It represents a nuclear dipole opposite the magnetic field. Since nuclear dipole opposed to that of magnetic field, and it has got a high energy associated with it. And Iz is equal to 0 on the other hand, means that there is no net dipole on the field direction. And therefore there is no change in energy. And lastly, Iz is equal to 1 implies that same dipole in the same direction in the magnetic field, and hence it has got low energy. So you have three different cases due to the three different value of Iz. Now, whenever whenever you are applying a magnetic field B in the Z direction, there will be interaction with the dipole moment. So that interaction is mu Z into Bz. Now the separation between the neighboring energy levels will be then delta E. So separation between neighboring energy levels we delta E equal to E mod of E plus minus Z EIZ minus EIZ minus 1. So the first one will be presented as G beta N IZ BZ minus G beta N IZ minus 1 BZ. So it will be a mod of G Bn BZ into J and therefore delta E by H will be equal to mod of G Bn Bz by H into Hz. This is based on spectroscopy technique. This is the basis of techniques of a transition of electrons. So what is happening here? It is a transition of electrons or nuclear spins between energy levels. Between energy levels. They are loosely referred as change of spin, and they were associated with emission or absorption of energy in the form of radiation. So they are associated with emission or absorption of radiation of energy delta E by H frequency. And since the frequency is proportional to the applied field, we can arrange in principle to study spin spectra in any region in the spectrum. So this is again proportional to the field applied. So we can study the spin of the spectrum. For practical reasons, the magnetic field is between 1 to 5 Tesla, and this is for the nuclei, and for the electrons it is 0.3 Tesla. So that will make delta E by H for nucleus as equal to 100 into 10 to the power 6 Hertz, and delta E by H for the electron, it will be 9500 into 10 to the power 4 Hertz. There's this electron spin spectrum for a considerable higher frequency. Is on the longer wavelength range. Thus the technique for the magnetic moment of the electrons in the same principle.